raise your hand. There you go. So, Kevin, no one left in the kitchen? Great. So, welcome back everyone to Platerai. Well, first of all, anyone new to the meetup today? Nice. Few people. For those of you who it's your first time, we host these meetups every month at Kensan. We try to focus on development technologies, front end and back end. So follow us on meetup.com and see which topics are going to be up. Suggest topics if you want to. Also for Kensan, we are a professional company, professional services company, specializing on cloud migration. And today we have a guest speaker from Spotify, Humphrey. So let's kick it off.
Thanks, Carlos. Thanks. So currently at Spotify, I'm a machine learning engineering manager. So I work closely with machine learning engineers who help personalize and optimize things on the free side of our product. So ads optimization and other commercial revenue opportunities around that. Once upon a time, and still in my spare time, I was a machine learning researcher though. So that's how I spent my first couple of years at Spotify after coming out of a PhD program at NYU. And when Carlos and I were talking about what might be a good fit for the meetup, one thing that I kind of settled on was this project that I've been pitching in / dragging through the mud for a couple years now. The idea being, so first off, Humphrey, some other collaborators on this project, Simon Duran, who's also at Spotify, Brian McPhee, who is now faculty at NYU, doing data science and other fun things, and then Julian Urbano, who is now is a information retrieval lecturer and expert. Now he's at TU Delft, but did a lot of this work when he was still at UPF in Barcelona. Okay, we all come from this community called Izmir. How many people have heard of Izmir? Right. So how many people know about NeurIPS? Formerly the conference known as NIPS or ICML. So there are a lot of international machine learning conferences. A lot of the work that deep learning has been done in has generally been done in images and text. You can also take those technologies and apply them to music. Whereas in computer vision, there are data sets like MNIST for handwritten characters, ImageNet for images from the wild that have different tags. We don't really have anything of that scope or scale on the music side. But we've been having conferences for 20 years, and one of the things that we've been trying to do with our machine perception algorithms around music understanding is benchmark how well they're doing. Because when it comes to so first off, come back to that. When it comes to trying to build out these different systems, you could think of your machine learning model as being the hypothesis for what you're trying to do. And this holds whether you're trying to pick out chords in music, or if you're trying to optimize which checkout flow your user might get in a web store. The model or the algorithm that you're presenting, it's kind of the thing that you put forward as your hypothesis. And then you can collect data against that to evaluate how well that is or isn't doing. In the chord model, you might say, you have a guitarist sit down and say, no, these aren't the right chords for this thing. On the checkout model, you might look at how many users successfully purchase your product, subscribe to your service or something like that. But all of this depends, especially when it comes to science, depends on reproducibility. So we, in 2016, had put together this plan for sustainable MIR evaluation. 2016, this is an important year because it's 2019 now. The community has done this kind of long-term benchmarking for a while. So the first year, this algorithm bake-off competition called MIREX, it's the Music Information Retrieval Exchange. This is modeled in the style of Trek. So a lot of search algorithms that have gone into systems at Microsoft, Yahoo, or Google. other kinds of NLP systems use that Trek model of evaluation. Murex is the music version that was built in the same idea. And over time, participation has really gone through the roof. And it's been really great for this music information retrieval community to benchmark the different algorithms we have. I'd pause and say the whole premise of why would you want to study music information retrieval, Spotify has 40 million songs and counting. It's something like if you tried to listen to it all end to end, it would take you something like 2,000 years. Like you cannot, no one can listen to all of the content that we have. So to be able to do true music discovery and recommend things that no one's listened to, we have to have algorithms that can understand that content. There are many other things you can imagine happening. On YouTube, people are uploading content all the time. SoundCloud is similar. We have this massive explosion of content, and we want these algorithms to be able to do this. Tell us really high-level information so we can do recommendation. We can help detect fraud if someone's uploading songs they don't have the rights to. These kinds of high-level things. So it's been great for us on the music side. And you can see all of the different kinds of tasks that you can do with music signals, and if you have enough data, machine learning. So you can try to say, from audio, can you identify what the artist is? Is it Queen or is it the Rolling Stones? Can you do different drum detection, kick drums versus snares and toms? Some of these things are really important for companies that work on digital audio workstations. So if you're doing a multi-track recording, if you can tell what's being recorded on each microphone, you can help with automatic mixing and these other kinds of algorithmically powered tools. Genre key, melody. Actually, is anyone familiar with GarageBand on Apple? You might have noticed GarageBand now, if you start playing a MIDI keyboard, it'll try to tell you what chord you're playing. That actually came out of some people who worked on the symbolic key finding stuff out of our community. So they've been working at Apple in London now for the last several years. So they've been putting machine learning stuff into production on that side. There are also things like cover song identification. Could you say, hey Spotify, give me all of the versions of Adele's Hello, even if the metadata might be wonky or something like that, right? Chords, tags, once upon a time query by tapping would be a way you could search for things. So there are all these different things and all these different experiments. And Murex has been really great for Izmir, but it's had this major challenge, and this is kind of where some of the cloud stuff, I think, for this comes in. Because we're working on music, and music is heavily copyright controlled, what we've had to do, or what we did for a really long time, was bring the computation into the data. So what that looked like is scientists would write code for their algorithms. They would test it out on whatever data they had locally, and they would lob it over the fence. This red line is a fence. And then we have these volunteers, who we call task captains, who take all of these different code implementations that have been rigged up on research machines. A lot of this, these aren't tech-savvy folks for the most part. They're not containerizing things with Docker. They may not have version control. Some of it might be in MATLAB. It's really all over the place. These task captains have to get everyone's systems running because we're withholding all of this audio signal data. They run everything, and they say, congrats, guys, here are the scores that you got. So-and-so has the best algorithm this year. And the scientists say, okay, that sounds good. But if we think about this kind of model, there are actually three main challenges that we've kind of stepped on in trying to keep this thing afloat. The costs for this, the computer time and the human labor. Brian's really good with the sidebars. The arrows are probably not to scale. But the compute time and the human labor to get all these things to happen, it takes a lot of people who have to do all this volunteer time to get their 30 runs across the board in a fixed amount of time while they have all their other stuff that they're running. And what ends up happening is this consumes all of the costs that people, especially in academia, might have for grants. It doesn't really leave much money left over for data collection. So the data you have doesn't necessarily grow over time. So actually, the worst thing that could happen is everyone learns about Izmir, and everyone builds an algorithm, and everyone wants to participate in Murex. Growth is the absolute worst thing that could happen to this model. And as I kind of alluded to, it's hard in this scientific feedback loop to get an idea of how well you're doing if you can't get a look at your data. You have results. You have this aggregate score, but you have no idea why you got that score. It'd be like taking a test and your teacher saying, you got a 70. You know, what do I improve? What did I get wrong? And you're like, you'll figure it out. So we usually have performance metrics. Sometimes we're able to get back what other people have estimated from their different algorithms, but we never really get a chance to look at the data because of reserving all that from the beginning. And it also ultimately ends up being a data deficient process. And what I mean by that is that there's no natural plan, sustainable plan for where we get more data. And when you don't get more data, you end up having a data bias. You end up kind of chasing the answers that you have. Even in the scenario where you take a test, you get a 70, and the teacher says, good luck, try again. If you keep taking the same test, you'll eventually figure out what you're getting right or wrong, especially if it's multiple choice. You'll start changing the things you're not necessarily confident on, and you'll eventually get that 100, but it doesn't mean you've learned anything fundamentally important. Because we have no idea of what the data is on that front side, we don't even really know what this bias is. So this is kind of bad for science. We're drawing these conclusions through a keyhole, and we don't necessarily know how to move forward. So it's inefficient, there's limited feedback, there's an inherent unchecked bias in the data. This is where it gets really interesting, because machine learning has totally exploded right now. It's blown the lid off a lot of companies' funding strategies, how they're building tech, how they're trying to incorporate it into their tech strategies. A lot of the progress that's been made in machine learning has actually been done on these data sets that have been built in the 90s, in the early 2000s. They've been well curated, they've been manually maintained. But if you are a company and you were trying to say, you know, there's this problem that I want to solve. I really want to do traffic pattern monitoring because we have all these drones and we want to fix these things. How do I bring machine learning to this? And you're like, well, we don't actually have any data. So what OpenMIC is fundamentally about is a sustainable strategy for getting labeled data so that you can bootstrap a variety of different machine learning problems. In our case, it's actually, so OpenMIC is the Open Music Instrument Classification Challenge. So we're trying to do instruments in audio the same way that ImageNet, this data set for computer vision, is objects and images. So how do we go about bootstrapping this building of a data set where we start from a standstill? We can look to Kaggle. Kaggle inverts the model that we've been doing for a while by bringing data to computation. So what you end up saying is that I build an algorithm, Carlos builds an algorithm, everyone else builds an algorithm. You run the prediction on whatever system you have, whether or not your code is version controlled, whether or not it's written in Java or MATLAB, and you produce outputs. You then take those outputs, you upload them to a system because you already have all of this evaluation data, and so that scales. The trick then becomes you have to have data that you can share. And this data is old now. Kaggle has since been bought by Google. This is a wildly successful data competition, machine learning competition platform. So rather than bringing computation to data, let's bring data to the computation. And this has worked in a number of other different scenarios. ImageNet is a really, really big one. Is everyone familiar with the deep dream, the really trippy images that neural networks have been producing recently? On the break, I'll pull up some images. We've been able to have a lot of these really crazy computer vision technologies come out of this data set, and this data set alone. Because we have millions to tens of millions of images that have these different object tags. And you can really start to get creative with how you take that data to solve different kinds of problems. On the open audio front, we need to have audio that isn't copyright controlled. And there are a few collections actually now. When Murix was started in 2005, it was kind of on the tail end of Napster. Anyone remember Napster? Kazaa or LimeWire or all the other BitTorrent and file sharing things. That was the best way people could get access to audio. But in time, the Free Music Archive is a collection of either Creative Commons or public domain audio content that musicians composed, recorded, and then just released for open distribution. Trent Reznor has some of his stuff in the Free Music Archive. It's not all Trent Reznor. Jamendo is another service that actually aggregates Creative Commons content for video game licensing, film scoring, advertisements, stuff like that. So Jamendo's a large collection of popular-ish music or at least popular sounding music that's been rights cleared for these different kinds of things. And these two collections in particular have around 250,000, and actually the Free Music Archive is closer to 100,000 tracks. So these are also relatively large web-scale collections. So in this distributed model, you want to distribute computation to everyone's computers when they're building their own machine learning models. The data is already out in the open, so if you might not necessarily know, you would still only get the aggregate score. You'd say you got a 70, but you could look at what your model produced on one versus another. And we're able to allocate best effort to the people who wrote the algorithms. We don't need these task captains or these shepherds to kind of plumb everything through. We still haven't solved the problem of where is our data getting labeled from. And this is the interesting piece from how do you build a data set for machine learning. So this leverages this idea of incremental evaluation. So you could imagine if you have 1 million data points and say just 5 models, what you could do is run those 5 models over your 1 million data points. Anytime that those models agree, labeling that data point adds no information because they're either all right or they're all wrong. So what you can do is you can re-rank all of these 1 million data points to be able to say which ones have the most information gained by getting that thing labeled. Because this is how I'm going to be able to tell these different models apart. So it's a way of prioritizing the data that you want to get labeled so that it adds the most information back when you train that 6th model. You have this iterative increasing ensemble method, if that makes sense. And actually in the music information retrieval community, we kind of backed our way into this, not so intentionally. So this has happened a few times for beat recognition, music similarity chords, and then some stuff around structure. The first time, you're going to have to label something cold because you don't have any models yet. And then the nice thing, like I was saying, is that this disagreement can be informative. So if you have 2 different models here, Bart and Lisa are different ML systems. If they're disagreeing, there could be something interesting or important about that. If you're familiar with music theory, an F major is kind of in an F7, the sus4, or at least at the 5th. So it overlaps a little bit. And you can use that to better understand how your system's behaving and what it's doing. So this is the grand recipe for how you build a data set from nothing, or at least for music. Identifying the Creative Commons licensed content, figure out what task you want to tackle. You pay to get an annotated development set built. This is the highest cost from the start. You have to have something to start with. You have to be able to say, I have 500 data points, I have 1,000 data points. And then you take an evaluation set that has no label. You take all of the data that you've collected, and then you throw the models that have been built on the development set at this evaluation data set. You can figure out the points of disagreement, and again, pay to get some of those ranked. You can tell which ones are doing better. You've produced a system that's probably doing the best. You then release that data that you paid to get labeled, and you do the whole thing again. So every iteration you do this, the amount of training data is getting larger and larger. And as your models get better, you have to label less and less. Because as your models get good, you can kind of trust those things. They say, this is all this thing, and we're all really confident. Cool. We can actually say that's a semi-supervised labeled data point, and you can start to move on iteratively. Okay, but from a science perspective, there have to be drawbacks, right? There's no free lunch. A big one is the loss of algorithmic transparency. If I give you 1 million data points and you give me a CSV file of 1 million rows, I don't know how you got that. You could have done it all by hand. Cool, thanks for all the manually labeled data. This is actually a really good thing that we now have because you just gave us quick data. So there isn't really an incentive for cheating. If it was easy to cheat, we wouldn't be here in the first place. You can also prioritize or incentivize open source implementations, submit things through GitHub, submitting systems on Docker. Yep, cheating's not really a thing. And then there are some questions around Creative Commons or public domain music. Is it really real enough? If you listen to some of it, especially in the Free Music Archive, a lot of it is very experimental. It's not Taylor Swift. Jamendo is a little bit more what you'd think of as being commercial quality, or at least more mainstream, I guess is a more appropriate way of saying it. But if you're doing tasks like what instruments are in the recording, what language is the performance in, the music's certainly real enough for those kinds of things. Cool, so that was 2016. 2017, we were really busy with other stuff and nothing happened. We spent a lot of time building out that initial annotation platform to try to get things annotated out of the subset that we had, but we didn't really make any progress. And when we went back to the conference, when it was in China, everyone kind of gave us a gentle ribbing and said, what happened? You guys published this manifesto, where did it go? So 3 things changed in the course of 2017 to 2018. Crowdflower, which is now Figure 8, has now been acquired, started working with us at Spotify to do some other tasks internally. Crowdflower is similar to Mechanical Turk. So it's a portal where contributors can come in. You build a human intelligence task or job or question or something like that. You put it in front of them. The nice thing, and they answer it, you can aggregate their responses, and you have something resembling a gold standard label or human truth or consensus. Or if you don't have consensus, you now know that this data point is ambiguous, and that's informative too. The nice thing that Crowdflower does is they go to great lengths to help you improve the data quality that you get back. Mechanical Turk, at least in the past, is notoriously, say, unstructured isn't the right word, but it's kind of very, very open. Crowdflower forces you to have certain checks. It builds in control questions that you have answered to make sure that contributors keep answering those questions with a certain level of quality. If someone drops below a certain score that you set, kicks them out. If they answer questions faster than you allow, it kicks them out. You only pay for work that's completed. There's a gating quiz. It has a lot of these nice guardrails that help you get really high quality data really, really fast. They, at one point, had something between like 1 to 4 million contributors globally. You can chew through some pretty large data sets quickly. And there are actually some companies, they have an API where you could actually have your data in real time through a series of callbacks be plumbed through to Figure 8. Humans will label it, and with whatever latency that takes, it'll eventually go back into your system. You could spoof a human intelligence system by having it plumb these requests out to Figure 8. It was Crowdflower for years, and it's really hard for me to say Figure 8. But I'm doing okay today. Anyway, also, Free Music Archive was a web service. They didn't really have an API, but some enterprising researchers went and downloaded the entire thing, which is about a terabyte of MP3s. And then they just put it on a CDN and said, here you go, world, we went and did the thing. And it's all Creative Commons and public domain content, so it was totally legal. They kept all the license information, they were adhering to the licenses, and that was hosted. You could go and download that, and people have started working on that as a rather large collection of audio. And the third important thing is Google released 2 things. AudioSet is a labeled collection of YouTube videos and audio to the tune of, I think it was 1 or 10 million different 10-second clips from videos. And they used a mix of both text around the videos with a little bit of human cleanup to share out that data set in a featureized form. That featureized form is this model, the neural network that they call VGG-ish. VGG-ish takes a second of audio and spits out 128 coefficients that are arbitrary. It's an embedding. That means nothing when you look at it, but it's an embedding representation of that audio. Now these 3 things combined allowed us to then build that development data set. So I'll pause in a moment of honesty to say this isn't entirely the cold start approach. We're bootstrapping some other stuff to get here. But you could do, if anything, this moved us further down the line faster. You could still apply basically what Google did. They kind of got us to step 2 in the process. So we started from second base and built out this data set that we call OpenMIC 2018. And now what we've been able to produce on the Free Music Archive is this collection of 20,000 polyphonic, so it's fully mixed music, it's not an instrument isolation, from the Free Music Archive that have been mostly deduped from artists, so you don't have to worry about any data contamination across the things. They're 10 seconds each. Um, they're, they have, they're triple labels, so it's the file ID, or the track, the clip ID, the instrument, and then a binary yes or no. So everything isn't labeled completely. That's why there are 40,000 labels. You can think of it as being like a mostly incomplete matrix. Um, if we had everything would have 400,000 labels. But what ends up happening is that you seldom have 20 instruments on at a time. Most of the labels are off at any point. So we were able to crowdsource these annotations using Figure 8, and we then turned around and were able to Creative Commons license the data set for people to do whatever with from there. So in words or bullets, what we did was we took audio set and were able to transfer that model to the Free Music Archive, a data set that didn't really have the same labels. We ranked these Free Music Archive clips by likelihood for the different instruments. We then sampled from the top 10% and the bottom 10% to say likely positives, likely negatives, 500 positives, 1,500 in total, and then kicked them out to Crowdflower. So in boxes, because of YouTube licensing, they couldn't share the actual clips from YouTube. They winked, nudged, kind of pointed to like a downloader that you could go and get things if you wanted to, and some people immediately went and then built web crawlers to pull down most of the audio set in its audio form. But they do share a large collection of those features. I think they're in like PDF records if you're familiar with TensorFlow or something like that. So we took those features in the labels, and then we built a few different models to this bootstrap labeling. Then come back to the Free Music Archive. Using something vaguely Kubernetes-ish, we mapped our VGG-ish feature extraction and then the model over the entire collection of content, the 100,000 things, and produced something like 7.2 million clip likelihoods. So we did a mostly like a 50% overlap stride to get these 10-second chunks. And then once you have these clip likelihoods, we did some clever sampling to try to optimize our selection across the different clips. So it's not just pick this one first, pick this one. We want to draw across both instruments and tracks in a way that we can try to minimize the amount of correlation or bias in the sample. We then take those clip likelihoods are tied to a file ID and then a start time and duration. We can go back, get the audio, and then put that audio out onto CF here, but it's Figure 8 now. And what that looks like is in doing the clip extraction, we're also doing, this is a spectrogram. A spectrogram shows frequency content, so low to high, as a function of time. So you can see there's a lot of low frequency content here, higher this way. There's been research that showed if you're doing audio labeling, images can be really helpful for non-experts to start to have that additional modality, be able to understand what they're hearing better. This is also really helpful if you're doing any time things. You can kind of see the beat here. These impulses across time correspond to the meter, the beat, the tempo of the music. So in this case, for every class, in this case it was mandolin. So we had 20 different tasks that went out to Crowdflower and said, we got our people who were able to do just the mandolin tasks. So they passed the test and they could give us all this data. Or accordion, banjo, and these other kinds of things. They're able to do that for about $2,500. We were able to get the 40,000 samples. And we actually, Figure 8's also really great because they give the contributors an opportunity to rate your job. So they can say, how easy was it? How clear were the instructions? How fair was the pay? And it can be really motivating to try to make all those things green. Contributors do not hold back if they think you are lowballing them on price or if you are not very clear in the job that you put together. So there is this nice kind of like market dynamics, but also collaboration between the two. I'd pause and I could go on for a while about things that Figure 8 does great. Um, if a contributor disagrees with your test question, they can contest it and provide a reason. And it's remarkable, some people who say like, that's not a piano, that's an electric Rhodes or something like that. And like the level of expertise and how seriously they take it is really impressive. Um, every contributor has a trustworthy score that affects them across all of their jobs and the ability for them to take different things. So they have this broader external incentive to do their best, which also means you can get by with slightly fewer guardrails at times, actually. They've built such a good incentive system around getting this thing right that you can kind of start to take the guardrails off and everyone still behaves. Cool, so we have this development data set. The next step is to take all of this stuff, go build instrument estimators, and what we're actively working on right now is we have the Jamendo collection. So we're going to try to transfer this across this bigger, more real data set. So we're going to pick out 250,000 10-second clips, share those things out. We have this very hacky app engine submission system. So if anyone is a JavaScript whiz, I don't know what I'm doing when it comes to front end. But here, this is working. So it's using Firebase to do the OAuth login. You can see I'm logged in here, my Spotify address. Right now, it's doing CSV, uploading and validating. There's a simple scoring function that's happening in the back end here. So ideally, what this will be is as people start submitting things, you would have this broader leaderboard. You can throw some D3 at it to get some nice graphs and stuff. But this is actively under development. And then, yeah, so people who have built models can submit these time-varying estimates over all these clips that we've shared. We'll then go get annotations based on the responses we got back, and then at the end of a competition window, announce a winner and maybe have a prize or something like that. So it'll be kind of Kaggle-esque, but more with the plan is to make the App Engine submission system fully open source, have all the metrics fully open source, have the data be fully open source. Cool. So how could you play in this competition? There's a starter repository there. We'll take a look at it after a short break. But that has a link to the data is hosted on a service called Zenodo. Zenodo is a really beautiful side artifact of CERN. So CERN has the large Hadron Collider. They apparently produce tons and tons of data. One of the things that they did was say, we have a ton of additional storage. As part of all of this EU funding we've got, we're also going to provide this free service where if people have data sets up to either 20 or 50 gigabytes in size, we'll host them free of charge because it's a drop in the bucket compared to what we generate. So the data is hosted on Zenodo. They provide DOIs, which makes it really easy to track which version you're downloading. I'm currently in talks with our FOSS board, the free and open source software team at Spotify, to get that App Engine thing cut over so we can have more external contributors on. It's supposed to be just a dead simple login thing. Currently going through Jamendo to pick out the bits that we do want to share out. We want to make sure, one of the things that we found is that if you throw a rock into a music collection, you tend to hit things like guitar and voice and drums and guitar. There's a much broader distribution of things out there, but it tapers off pretty quick. So we want to make sure that we're casting a net and getting a broad, different cross-section of things. Hopefully this summer we'll actually go live with this, and we'll be able to have like a 2 or 3 month submission window, just like how Kaggle does. Competitions start, you'll have your 30% validation leaderboard, and then you'll see the clock tick down and stuff like that. We have an email address. I left it there because I want to remind myself to go check it. I don't know that anyone checks it, but I'm very active, or at least I'm aware on the PVD Geek Slack. So if you join that, you can also find me there. I also have business cards, and I'm EJ Humphrey at all the places. So thanks. If anyone has any questions, we can do that now. Otherwise, we can break for, say, at 7:15, we'll reconvene. And I'll try to do a live demo of what it would look like to install that repository on your machine and start training a simple machine learning model on music data. Cool. Thanks.
Questions? anyone has questions about presentation? Okay, well, we're gonna take a break. Eric will be around. We have a few people from Kansas. If you guys need more info about us, Isaac is back, and Harlan. They are our people and culture team. So anything about the company, if you're looking for a job or anything, talk to them. And we'll see you in 7:15.
7:15, 8 minutes.
before I forget, everyone, if you guys want to be part of the active community in Rhode Island and you haven't joined PVD Geeks, you can go to pvdgeeks.org and request a invite from Brian Jepson. So actually, we have a Slack channel going, and we try to get the Rhode Island community engaged for various different groups. We have Prog.js in there, we have Planerai, we have Tech Collective there. So you can actually find out about more events. There's always something happening in Rhode Island, so join us there. And then also OpenMIC, it's open source, right?
Yep.
So if any of you guys are looking for anything to work on or to add to your portfolios if you're a new graduate, you can just contact Eric and
definitely ping me on the PVD Geeks Slack channel. My email inbox is trashed. It's really bad. I want to set up an auto reply to just say like, find me on one of these Slack workplaces. Yeah, it's pretty bad.
Okay, so
awesome, thanks. Okay, so I'm going to try to go through this really quick, and I have no idea how this is going to go, but we still have everything building on Travis, so I'm expecting good things. So this repository is kind of like the landing page for the data set right now. If you go, Cosmere is community for open source MIR, music information retrieval. OpenMIC 2018 is the data set that we published this last fall. What's in this repository is, other than a bunch of Travis boilerplate, is this library that gives us the Python library that gives us a convenience wrapper around Google's VGG-ish model. We'll take a look at that in a second. There are no guarantees that it would be stable, and it could be kind of difficult to take that model if you're not familiar with TensorFlow or audio signal processing to go from audio to time-varying coefficients or numbers. So we provided a slightly simpler API for that. In examples, there is a IPython notebook. If anything breaks in the course of trying to install this, I'm going to just walk through that notebook and then figure out why it broke. But cool. So there's some links here. Actually, let me pop this up into Zenodo real quick. So if you follow this through to Zenodo, this data set contains the following: 10-second snippets of audio in a directory format like audio. This is the first 3 characters of the file name. Some people have to worry about inodes. When everything lives on cloud storage, it's not so important. But that kind of groups things into these sub-buckets based on the indices are up to 7, because it's just decimal numbers. 6. So there are 100,000 things. So that's just a 3-character prefix and then the full key there. We've pre-computed these VGGS features, and they're stored as JSON. So if you want to use PyTorch, or if you want to use something in R, you're not restricted to stick to any kind of Python-specific thing. We provide, in this library, there are some test utilities. I'm not going to go into that because it's not worth the time. But to make sure that the MD5 checksums of the OGs and the JSON are consistent so that you're like, yes, I have the thing that I was promised. This is sometimes a problem in research data sets. We have the anonymized individual responses. So what contributor, all the contributor IDs have just been assigned arbitrary hashes. So you can still group based on those things, but we want to protect all the contributor information. So that says what the contributor said, over what input, at what time and in what order, kind of thing. We aggregate the labels into a more useful rollup. So that is the clip ID, the instrument, and then a value between 0 and 1. 0 is that it's not there, 1 is that it is there, and then you get some scalar sense of any kind of disagreement between that. There's subtract metadata with the licenses, because with Creative Commons content, you have to make sure that you're adhering that. But if you are going to use Python, we roll all that up into a nice NumPy zip archive format, so you can open that thing and have everything in more of a scikit-learn style format if you're familiar with scikit-learn. So we can back that into NumPy arrays, and you can move pretty quickly with it. And then we also provide partitions. Partitions are important to make sure that what you're training on does not contaminate what you're testing on. Instruments and artists tend to be very correlated. So if you have the same artist in your train and test set, you might be overfitting that it's just that same artist. So you want to make sure that you do what's called an artist conditional set, a split, so that you are making sure that you aren't falling into any of these trivial biases. The whole thing is 2.6 gigabytes. The Python NPZ itself is around 200 meg.
How are you making those sample partitions? Is it just through your own curating, or is it based on previous runs or something?
So Brian did the stratification.
Okay.
I believe it's as simple as figuring out where you shuffle at the artist label, assign artist to folds, and then things go back. It's supposed to be that every clip comes from a different artist, which is why there are only 20,000 out of the 100,000. In the Free Music Archive, you'll have some artist has one song, some artists have 100 songs. So we try to go through and pull one track per artist. So in general, we shouldn't have to worry about that too much. And then we also want to make sure that this is why it's more interesting. The sample partitions are also trying to preserve instrument distributions across the sets, so that you have the right representation of mandolin and train as tests. Because you don't have to. It's already hard enough. We're trying to take things in the same MNIST route for the character sets, where it was like, by having a train and a test split, everyone can use these same train and test splits, and you can report against the same things, while making sure that everything is distributed as good as it's. So after we download this 2.6 gigabyte thing and we untar it, you'll end up with something that looks like this. Hooray, it's all there. Now, I use Conda. I'm a Conda fan. I know some people use PipX or PipC or other. I still like Conda. It's just everyone's weird. But you want to make this much larger. Okay, so the first thing I'm going to have to do, this is a new laptop, is go back and actually clone this repository. I think my public keys are fine. Great, we're already doing good. Installing the library is a little bit non-standard because we package the VGG-ish model parameters kind of large. I think it's like 80 or 100 megabytes. And they're provided on a CDN that Google provides. And we can't easily put them into the GitHub repository. You could use like the Git large file format, like Git LFS or something like that. But for an open source project, the price point was not manageable. So 2018. Please still be there. Please still be there. Great. So you'll see the first thing I did was moved into the directory itself, and then you can call this download dependency script. The VGG-ish model is two different things. The first thing is, let's see, dot checkpoint. That's the parameters from a TensorFlow model. So when you design a neural network, you have, in the simplest form, a bunch of matrix multiplies, some arbitrary depth, and you have all these coefficients. In TensorFlow, each of those matrices gets a name, and they get bundled inside of this archive. So when you create that model in memory, you can then say, take that checkpoint and reload it back into the neural network. kind of like if the neural network is the Sega Genesis, the model is like the cartridge that you plug in, right? And that gives you this model. But the last thing that the researchers at Google did was they said it was producing a pretty large output dimensionality. And they said, well, what we'll do is we'll compute a statistical dimensionality reduction to get it to the most important 128 coefficients. It's called a principal components analysis. And it's a nice linear algebra operation that is pretty common in data science and statistics on matrices stuff. So those are the two parameters, the model itself and then this dimensionality reduction, the PCA. Now, once we've downloaded those things, we can pip install from the directory. And what it'll do is take those two files and bundle them up in the library using package resources to make sure that you can still access it from anywhere on your environment. So that you don't have to worry about being in a certain directory when you're messing with these different things. While that's doing its thing. Great. So at this point, everything should be installed properly. Do I run the tests? Run the tests. That'd be fun. In the meantime, if we pop over to this, what I'm going to open in a second is this Jupyter notebook. This is all in Python 3. I would expect that some of this might not work in Python 2 because of NumPy serialization, but leave that as an exercise for the curious reader. You'll say download the data set. We're going to load in the VGGH features and the labels. We'll fit a random forest model. So random forest is an ensemble method of decision trees. We're going to fit one model for each instrument class. So there can be one versus a number of binary estimators. We'll do some simple evaluation, and then we'll show how to say if you had an MP3 on your hard drive and you wanted to run this thing on it to get output estimates, how you would do that. Important disclaimer, this is not meant to be state-of-the-art. It's just kind of the proof of concept. The hope is that using this starter data set, you could build whatever crazy machine learning model you want, maybe going back to the audio, using any number of data sources. The VGGH features are good, but they're also limited based on whatever that model was initially trained for. And it was more generic than music instruments. It was a general kind of like sound texture model. Cool, so that did its thing. Sweet, so far this is going well. All right, so the first thing I'll have to do is update what we call the data root, which just specifies where that archive was unzipped to. So that should be the audio and the features and everything else under that. Is that guy? Sweet. So now we've loaded this, and we can look at what's in the keys. We'll see there's an X variable. Well, X is a matrix, Y is a matrix, Y mask is a matrix. I'll get into Y mask in a second. Oh yeah, there's a bunch of. Who saw those numbers? Great, no one's paying attention. For a Spotify sticker, what do you expect the dimensionality of X to be? X is the features, they're VGGH features. How many audio samples are there in the data set? 20,000. And then what's the dimensionality of the VGGH features? 128. And you get one coefficient every second. So what's the rank of this object? So it should be, yeah, here we go. Everyone who said, you got it works really well in like team meetings too, but with not Spotify stickers. We have to do swag and stuff. Yeah, so there are 20,000 data points. There are 10 seconds per clip, and there are 128 coefficients per second. So you could, for any one of these, look at the coefficients over time. Because it's only 10 seconds, there actually isn't that much variation usually. And what you can end up doing is saying like, well, what is the average coefficient over the 10 seconds? You could take the mean over the second dimension. Similarly, in Y-true, we have a two-dimensional matrix. So there are 20,000 rows by 20 columns. In the, so if you were to index it, say 40, 4, it's the confidence that example number 41 contains the fifth instrument in the set. We also provide, I'm going to go out of order. So because we're using these positional encodings for the model, you have to also provide this class map that maps human readable names into the actual integer positions in the matrix. So the fifth instrument, I said 4, so the fifth instrument would be the clarinet. Now, we also have to provide what we call a mask, because in this matrix, we have values that are 0 to 1, and then also a bunch of nands, because we have missing data. Because we didn't compare every clip with every instrument. That would have been another 360,000 comparisons. Because we know or assume that they're mostly off. So we have a mostly empty matrix. And the mask is a way of plucking off the things that were labeled. That's how we can easily drop our nands. The sample key is how we can map back from integer position back to what audio file it corresponds to in the set. So I will start blowing through these things. Oh, it's been a while I haven't spoke. Not nands. If we don't know, it's a 50% confidence label. Because you're saying it's a coin flip that it could have this or that. And we use the mask to pick off the ones that weren't labeled. Because we want the bias point for every estimator to be right in the middle if we don't know what's in there. We don't necessarily want it to be the frequency it occurs in the data set. So here you can see 0, 1, 2, 3, 4, 5. Here, this was labeled for clarinet and else nothing else. So this only has one known positive label. Actually, it's one known negative label. This is unlikely to have clarinet. And then we can go and look at the audio for that one. So if we were to say, they're OGs. I apologize. You have to listen to them in VLC. Cool, no clarinet. We're doing great. Science, it's happening. It's alive. Anyway, there was one time when I was working on my PhD, there was we had a visiting PhD student from Germany, and I came into the office one day and he was looking really dejected and he was like, "Do you ever listen to the music that we work on?" And I was like, "What do you mean?" I was like, "I listen to music all the time." He's like, "No, but like, we work on music, and so often it's just we process the bits, and then we run the numbers, and we do this. It's like, we don't listen to this stuff nearly enough. And he was working on like Chopin mazurkas because Chopin mazurkas are very expressive in their timing. So they get really fast, and then they slow down. And they wreak havoc on machine understanding of tempo. I always think of that whenever I actually go back and finally listen to music and any of the music research stuff. It's like, yeah, you should really spend time getting to know your data. Which is less appropriate if you're doing like ML on health stuff, but music is generally nice. You don't have to worry about the privacy things as much. Cool. So what we've done here is we have these partitions, which are, you can see they're indexed by these sample keys. Side note, the sample keys, we've written them, so this is the original index in the FMA underscore the time in milliseconds that it was drawn from. So if you wanted to get back to the original clip to say where did this thing come from, you would say, 3.8 seconds in this clip is where this was drawn from. See how many are in train and test. In this partition, we have slightly more than 25% for test. And we can map these back to just sets so that we can, if we wanted to, we could make sure that they would be disjoint. Here we build two integer arrays so that we can index the matrices themselves, and then we can slice out our train and our test. So here, if train has 14,915 file keys, we would expect that we have 14,915 data points times 10 seconds times 128 coefficients. This gets a little bit big, but what we'll do is throw some line numbers on there. What we're going to do is we create an object for all the different models. We're going to train one model per instrument and then key the model by the instrument name. Yeah, so we look at the instrument in the class map. Here, because this is a dictionary and we're iterating over the keys, this will be the instrument string name. So we can look up what its index is. Here, we're going to pick off just the mask for train and test based on that instrument index. Yeah, and we'll do, right. Now what we're going to do is we're going to subselect the features that correspond to clips that were actually labeled. So this is going to be the size of this tensor. Tensors are three-dimensional or more matrices. This size is going to vary based on how many things were labeled for every instrument. So if we have 1,500 clarinet, maybe like 1,700 voice, and 1,200 guitar, that'll be the length of this thing at every iteration, because the number of things that got labeled isn't consistent because of how the sampling ended up working out. Here, instead of doing the time-varying features, what we're actually going to do is look at the average coefficient over the 10 seconds as a simple model going forward. So here we can say, given these training features for the instrument, we'll take the axis, the mean over the first axis, which corresponds to time, and now we're going to have, this will end up being something like 1,500 by 128. We can do the same thing to get the labels, and after we go through all of this data mangling, we can fit a machine learning model. It's like really easy, right? In scikit-learn, they've built the API to be really user-friendly, so as long as you can get your features into a matrix and your labels into a vector, you can use a random forest classifier, you could use support vector machine, the latest hotness that they've implemented inside the library. But they all have a common kind of polymorphic interface. So you can do a lot of the same things, such as you can fit, you can then call predict. We're going to run predict on the train. So this is how well we are able to fit our data. We can predict on test. We can see how well we're able to generalize. And then we're going to print out how well we did on both of those. And I'm not going to run this in the interest of time, because I have to go to Staples. Apparently it takes like an hour to print a picture. Anyway, who knew? So if you run this, you'll see generally what we'll find is that it fits the training data really well, and you're going to see that it doesn't generally generalize as well. So this makes sense. If you were getting, for this approach, if these numbers were any higher, something would be suspicious. But this is kind of a ballpark to say, like, yeah, you know, for accordion, we trained on here 1,500 things, we predicted on 538, you know, 4 out of 5 are right. Same for banjo, bass, cello, clarinet, cymbals, drums, on and on. So we trained all 20 of these things. Now, if we wanted to predict any old audio file, SoundFile is a really nice library that has native OGG support. OGGs are kind of like the open source version of an MP3. We use them all over the place at Spotify. They sound great. So SoundFile is great for OGGs and waves. I don't think it has native MP3 support. This is our VGG-ish wrapper for the library. So it has a similar kind of, I believe we even called it like predict or something like that. Chain features. Yeah. So here, if you had, this is a NumPy array representing the audio, and then the sample rate for the audio. Sample rate corresponds to how many samples you've plucked off the waveform per second. You can then pass those two parameters into this very convenient function. It's called waveform to features. And this abstracts all of the TensorFlow rigmarole. And that stuff gets imported. It restores the parameters the first time you call it. So it's doing a little bit of caching behind the scenes, so you only eat that startup cost once. It spits out the time points corresponding to the features. We'll see, we're getting, this is a 10-second clip, we're getting features that start at 0 up to 8. It's actually like 960 milliseconds, but it's observing a second at a time. We'll see we have these features. We could listen to the audio using the Jupyter audio widget, and then we can look at the probability that that clip that we loaded contains any of these instruments. And we say, actually, stop it, you. Into a furious frenzy of no. So here it's thinking cello kinda, maybe piano, maybe voice and violin. So it's, and then it's saying definitely not mandolin, definitely not guitar. Who would have thought the flute might have been higher? But you get the idea of kind of, now you could take this and map this over much larger things going forward. And with this data, you can turn around and say, well, we did some pretty naive things here. We're averaging features over time. We're using a random forest. Random forests, they can fit the data really well, but they don't necessarily smoothly interpolate your space. You might even try a logistic regression model or something like that. You could run them on your own favorite songs. You could say, I know this has cello in it. How bad is this model? How much is this guy lying to me at the meetup? And yeah, and then right now, I believe we're thresholding everything into a binary, but you could actually use the label uncertainties to incorporate that in the model. So this is a starter notebook. You can take it, download things, run it all at home, maybe download the things overnight when you're sleeping or having dinner with your family. It might take a second, but Zeno is quick. I have 90 seconds for questions. One question.
What music do you listen to when you're working on machine learning?
I listen to a lot of like instrumental epic post-rock, like Explosions in the Sky, or even lighter stuff like, how do you say it, Valmaria? Or if this could destroy, like this could destroy you, kind of thing, or something like that. You know, this is like angsty instrumental rock. Thanks for being a little guy. Yeah, you get a sticker for that. Now who wants to ask a question?
Instead of no, hopefully this isn't off topic or anything, but so do you guys find a way, or are you planning on finding a way to, like, I just noticed that synthesizer is like one of these
High-level
one of the words
categories.
up there.
Yeah.
Is there any, if you, for instance, were trying to analyze like dance music or techno or something, would drums pop up in that somehow, or like did you find a way to like further refine these like individual sections that you had?
So the high-level plan is if we could get this to be basically perfect, we'd be like, cool, let's get all the guitar, and then we're gonna go to Guitar Center and be like, is this a Fender or is it a Gibson? Like, can you tell me whether it's like a Soldano head, or are we talking a Mesa Boogie here kind of thing, and really dial in, because we've already narrowed it down to a thing that we can really get those experts out. So then we can go to a bunch of synth heads and say like, all right, is it FM or additive? Like, what are you talking about here? This already is a pipe dream. Part of why we ended up at this taxonomy is because we were able to piggyback it from the audio set work. There were very long RFCs about like what instrument is in, what instrument is out. Like tabla is really important, but we can't find any data for it. So it's kind of like, it ends up being a compromise, and lean research is a thing, like build, improve, and iterate, and these other kinds of things. Like a lot of research gets stuck in that analysis paralysis kind of bucket. So doing something, and like we used FMA. I would never use that as the starting data set right now. It wasn't until after we get it all labeled that we were like, this is some weird stuff. But we just saw it through and we're like, it's a start. And by kind of embracing the imperfection in it, it's like, yeah, we're going to do this again and again, and we're going to version control everything, and we're going to have tests, and we're going to make sure that, by the 6th time, it's going to be great. So, and on that inspiring note, I'm going to go. Thanks.